Alright, in this video we'll be looking at the addition of acetylide and cyanide ions to carbonyls. So that would be the addition of acetylide. In fact, we'll just start with the addition of acetylides to carbonyls. Now, of course, we've already seen how we can take a terminal alkyne, convert that to an acetylide ion using sodium amide in liquid ammonia. But this acetylide ion can also be reacted with carbonyl through a nucleophilic addition. This negatively charged carbon can attack that carbonyl carbon, pushing the electrons up to the oxygen. Then with an acidic workup, you can form the alcohol. And so once we have this alkyne added to our carbonyl and forming the alcohol, we can go and do other reactions such as reducing our triple bond to a double bond or a single bond. But this is another way where we can form a carbon-carbon bond, is by forming an acetylide ion and reacting that with a carbonyl to form this alcohol. So the addition of a cyanide ion to a carbonyl follows essentially the same mechanism. That we have, say, a ketone in the presence of a cyanide ion, and with hydrogen cyanide, it's an acid catalyzed reaction that will get what is known as a cyanohydrin. And that has a nitrile and a hydroxide group bound to the same carbon. And again, we'll go through the mechanism. We'll see that it's very similar to the addition of acetylide. In this case, the negative charge is on this carbon, so that carbon can attack our carbonyl carbon, kicking the electrons up to this oxygen. And because we also have hydrogen cyanide in solution, the oxygen can deprotonate a molecule of hydrogen cyanide. Forming our cyanohydrin. Now, we don't have to do this reaction with just hydrogen cyanide. We can increase the concentration of cyanide ion by adding sodium cyanide or potassium cyanide or other cyanide salts. That it would introduce more cyanide anion and push the equilibrium towards the cyanohydrin. But because this reaction does use cyanide, it's potentially a very dangerous reaction to perform. And so it needs to be performed very carefully inside a good fume hood to keep that hydrogen cyanide under control. And so once we have a cyanohydrin, we can use that to form other compounds. That's what makes cyanohydrins useful. For example, one mechanism that we'll go over eventually has to do with the equilibrium reaction, that if we take a nitrile and we put it into acidic aqueous conditions, then we'll get an equilibrium between the nitrile and the carboxylic acid. This carbon here becomes this carbon here. And so if we did this same reaction with cyanohydrin, then we can convert this nitrile carbon to a carboxylic acid. And this will be known as an alpha hydroxy acid. And the reason it is called an alpha hydroxy acid is because this carboxylic acid contains this hydroxyl group on the alpha carbon to the carbonyl. And so whenever we have a carbonyl, the carbons immediately adjacent to that carbonyl are referred to as the alpha carbon. So this would be alpha, over here would be beta. This would be a beta too because it's next to the alpha. But anyway, another reaction, if we take this a step further, and both of these steps require heat, but if we have more heat, stronger acid, then we can dehydrate this hydroxy acid, wind up with a double bond, and form the alpha, beta, unsaturated acid. Because now we have formed a double bond between the alpha carbon and the beta carbon, creating the alpha-beta unsaturated acid. Now there's another reaction that we can do with nitriles, and that is the reduction of the nitrile with lithium aluminum hydride to form the amine. And so if we form if we add a cyanide to a ketone to form cyanohydrin, then we can reduce that cyanohydrin, we can reduce this nitrile group to the amine, so that gives us access from nitriles and cyanohydrins to amines. And so we can get, these are examples of some of the different functional groups we can achieve after the addition of cyanide to carbonyl. The alpha hydroxy acids, the alpha beta unsaturated acids, and amines, allowing us to create a variety of molecules.